All right. So we left off last class looking at Bayes' theorem. So we'll work through another example. We'll then kind of go over some stuff that looks really similar to other things that we've already done. But before I do forget, at the top, I wanted to mention, so I will, after class today, be posting kind of an online quiz that'll be due before we start class on Friday. Okay. So when it comes to those quizzes, they're always due before we start class. And if they're late, they get counted as 0, right? So you need to make sure you get that done before we start class on Friday. And that'll pop up as soon as I get back to my office, okay? So last class, we had this Bayes' theorem, which was a situation where we had 2 states of nature, 2 different outcomes that indicate, which of those states of nature we're in, right? So here was kind of the general version of the formula. All right, so we'll think about another example where, let's say we gave everybody a truth serum if we suspected they were guilty of a crime. Right? So kind of told a couple things about this test. The first is that given that someone's innocent, the truth serum makes them incorrectly say they're guilty about 1% of the time. And given that the person's guilty, the truth serum basically fails to work, so they still remain to say they're innocent about 10% of the time. We're then told the probability that any one person chosen at random is guilty is 0.05 or 5%. So if the truth serum indicates that someone's guilty, what's the probability they're actually innocent? So that's what we're looking for. So we're going to do a couple things. So the first thing we're going to do is just write out kind of what we're given, right? So I'm just going to kind of transfer some of this over. So the probability that someone's guilty, I'm just going to shorthand guilty with G, innocent with I, 0.05. The probability that given someone's innocent, the truth serum makes them say they're guilty is 0.01. And then given that they're guilty, the truth serum makes them say they're innocent with a probability of about 0.10. And what we're looking for the probability of is that given the truth serum makes someone say they're guilty, what's the probability that, not that they're guilty, what's the probability that they're actually innocent, right? That's kind of what we're looking for. That's what the question's asking for, okay? So we can look at this, and really what we're thinking about is, here's a state of nature, and here's an outcome of the test, right? So if we go back to the general form of Bayes' theorem, that's exactly what that's saying, right? So the state of, what's the probability of a certain state of nature given seeing a certain outcome on the test? Okay. So we're going to go back, and I'll blow this up here in a second. So notice here, right? Given certain outcome of the test, what's the probability that the state of nature is, whatever we're interested in. So here's kind of what we have, right? So I want to find this probability, right? So what I first need to do is write out that general version of Bayes' theorem in the context of my example. Okay? So I'm just going to look at this general form of the equation down here. I'm going to just start writing it out in the context of my example. So I need to give myself a little bit of room. So I'm going to go down here. So the probability of S1, well, my state of nature, or my S1 is that someone's innocent. So the probability of S1 is the probability that they're innocent, multiplied by the probability of E given S1. So times the probability of E, truth serum makes them say they're guilty, given S1, which is that they're innocent. I'm just writing this out in the context of my example. Now, I mentioned last class, the first part of my denominator is the exact same thing as my numerator, so I can just kind of rewrite that down here. And that kind of represents people who confess to the crime but are actually innocent. The other group of people, the other part of the denominator is people who are going to confess to the crime but are actually guilty. Right, and when we write that out, we'll see that. So the probability of S2, well, if my first state of nature is that someone's innocent, my second state of nature is that they are in fact guilty. Multiplied by the probability of E given S2. Well, my E outcome of the test was that the truth serum makes them say they're guilty, given S2, which is that they actually are guilty. Okay. So all I did here was write Bayes' theorem out in the context of my example, right? I was looking for a conditional probability. So I knew that I could rewrite that using Bayes' theorem. Okay. Any questions there before we keep moving? And I'll write this in red. So I was only directly given 3 probabilities, right? So if I start plugging these in, well, I don't have the probability someone's innocent, but I kind of know that, right? So if the probability of my first state of nature that someone's guilty is 0.05, what's the probability of my second state of nature, which is that they're actually innocent? What did we say about the 2 states of nature in these Bayes' theorem examples? They're the only 2 possible states of nature, so these should add up to what? 1. So this probability would be 0.95. Right? I'm either guilty or I'm innocent, right? So if I take the probability I'm guilty plus the probability I'm innocent, that should add up to 1. So if I know one of these, I inherently know the other. So the probability that someone's guilty, 0.05, probability someone's innocent, 0.95. Given that someone's innocent, what's the probability the truth serum makes them say they're guilty? I have that up here. That's just 0.01. The last thing that I need is, given that they're guilty, what's the probability the truth serum makes them say they're guilty? Well, I wasn't directly given that, and I wrote 10 there. I think I just wrote over my decimal, right? But it was supposed to be 0.10. Well, if I condition on the same state of nature, when I look at the different outcome of the test, right? These 2 things, right? If someone's guilty, they're either going to confess to the crime or they're not, right? There's only 2 possible outcomes for the test there. So conditioning on the same state of nature, looking at the conditional probability for the 2 different outcomes of the test, these should add up to 1 as well. So I know this should be 0.90. Now I have the only, the missing component that I needed. Okay. Any questions on that before we keep moving? Now I could have also up here found one more problem. I didn't need it, but if I conditioned on the same state of nature and look at the different outcome of the test, I know these will add up to 1 as well, right? Conditioning on the same, like, given that someone's innocent, what's the probability truth serum makes them say they're guilty? What's the probability the truth serum makes them say they're innocent? Well, those are the only 2 possible outcomes. So those 2 things have to add up to 1 as well. Okay. So usually in these problems, I'm given 3 probabilities directly, but as a result, I indirectly know an additional 3, right? Which is the ones that I wrote here in red. Okay. Questions on that before we keep moving? So now that I've got these numbers plugged in here, it's just a matter of getting this entered into my calculator, right? So, oops, we got to scroll down a ways. Here we go. All right, so this is kind of what I had written out, right? Maybe it's a little slightly different form, like shorthanding things. I had to look for what I was missing. Now that I've got that, I can plug everything in and get that conditional probability, right? So once I plug all my values in, it's just a matter of getting this entered into my calculator. Okay. Any questions? We're keep moving here. All right. So what if I then asked another question? Same setup, but I've got, okay, now the truth serum indicates guilty. What's the probability they actually are guilty? Right. Well, we go through, right? We now say, given that the truth serum indicates guilty, what's the probability they actually are guilty? So now I've got a different state of nature, same outcome of the test. I could write out Bayes' theorem in the context of this example, or I could or I could use some work I've already done to save myself a little bit of time. So instead of writing this one out in the context of Bayes' theorem, right? Here's another thing that I haven't really showed you yet. So given that the truth serum indicates guilty, the probability someone was actually innocent we had in that slide was 0.174. That's what we had already found. Okay. The new thing that we want to find is, okay, given that the truth serum indicates guilty, what's the probability the actual person or the person actually is guilty, right? Well, notice here, I'm conditioning on the same thing, right? So if I've got somebody and I say, okay, the truth serum made them say they're guilty, the probability they're actually innocent, given that information, is 0.17. So given that information, what's the probability they're actually guilty? Well, there's only two states of nature. So once again, if we're conditioning on the same outcome of the test, the conditional probability for the two states of nature have to add up to 1. Right? Given that the truth serum made me say I'm guilty, I'm either innocent or I actually am guilty. All right, so those two conditional probabilities, because I'm conditioning on the same thing, have to add up to 1. Right? It was the same idea as when we conditioned on the same state of nature, the two outcomes of the test. Right, same state of nature, the two different outcomes for the test have to add up to 1. If I condition on the same outcome of the test, the two states of nature have to add up to 1. So here, that would just be 0.826. Is it clear what I can do there? Any questions on that? Okay with this? Okay. So, you can kind of imagine, this true serum example kind of seems stupid, a little bit goofy. But you can imagine, if I just replace that word with jury, right? If I replace the word of true serum with jury, right, we actually get something that's really applicable, okay? So the first thing I might think of is, given that someone's guilty, what's the probability that the jury, finds them innocent or incorrectly lets a guilty person go free, right? Well, we can look back at some old court cases, right? Like before and after DNA evidence, where we can look at some of the cases where someone actually was guilty, like we found out after the fact, and the jury actually found them innocent. So we can get an idea about these probabilities looking at historical court case data. We can also look at situations where someone was innocent and incorrectly jailed, right? So same sort of thing. We can look at cases where after the invent of DNA evidence, or just things came out about the process, we can see how many of these cases were incorrectly, or people were incorrectly found guilty. We can look at some historical court case data to get an idea about that conditional probability. And then we might be interested in something like, given that a jury finds someone guilty and sends them to jail, what's the probability they're actually innocent? Well, within there are these conditional probabilities that we can kind of get a good idea about what those are based off of historical court case data where they've been overturned, right? Overturned. And so we could actually kind of find these probabilities if we had the data, plug it in, and actually figure out, what percent of prisoners are actually innocent, right? Which seems like a pretty, reasonable and a relevant question to a lot of people. Right? So I think I had kind of my given guilty, jury finds them innocent; given innocent, jury finds them guilty. Right? So Bayes' theorem has a lot of real world applications, right? Anytime we have a certain states of nature and we have some type of test that's trying to get at what the state of nature is, we can apply Bayes' theorem. Okay. So any questions before I take a little bit of a turn here into a new topic? Okay. So we're going to start talking about something called random variables. So it's going to be very similar to what we've already done. A little bit of a caveat to it, right? So random variables are going to be some experiment that we're running where we have a numerical kind of outcome, right? So we'll only focus on discrete random variables. There are also continuous random variables, but we're not going to do anything with those until after the exam. Okay? So a discrete random variable, right? The way we're going to notate this random variable is just a capital X, right? So maybe this is something like, I'm asking, or I'm recording the number of kids in a household. I go to a random household. I don't know what the response is going to be. I know it's going to be somewhere between 0 and 20, right? I know I can't have half a kid. Well, at least hopefully I don't have a response of half a kid, right? So I know that I've got these integer values and it's going to be discrete. Excuse me. And I know that I can see these different outcomes for X. So I could see X be 0. I could see X be 1. I could see X be 2. So there's all these different possible outcomes for X. Okay. So if it's discrete, right, we said these are integer values. We can kind of think about, I've already showed you this slide basically in the past, right? We can see the integer responses. We can't see anything in between. So the number of times or the number of days you do something in a week, once you do something on a day, you've done it once, right? You've done it on one day. So I could see 0 through 7 there. Can't see anything in between. So this is the idea of these discrete random variables. It's very much like just like discrete variables we've talked about before. It's just that we haven't realized the actual outcome yet. Hasn't, the experiment or whatever you want to call it, hasn't been run. Okay. Now we'll skip over continuous because, like I said, we're not gonna. I'll show you this slide after the first exam. But we can think about, family size is a real good option of a discrete variable. Distance would be continuous. Like we already talked about this with non-random variables, just general variables. But one thing that's kind of interesting we can start to do, and I don't think we'll get any examples of this today, but we can actually take qualitative variables, so like pet ownership, and you can just assign different words, numbers, and actually kind of use the same sort of approach that we would use for a variable that started out as discrete. So we can kind of turn qualitative variables into discrete variables here as well. That's kind of creepy. So we have this random variable x, right? It can take on all these different outcomes, and we know that some are going to be more likely than others. So we're going to have a probability distribution, right, that tells us which outcomes are more likely, which outcomes are less likely. Okay? So how do we get this probability distribution, which we can see like in a table or a graph, or even I'll introduce at the very end of class a specific type of a discrete random variable that has an actual functional form. So a lot of times when we think about these probability distributions, we're really graphing out this probability mass function. Now this probability mass function, if we put in certain values for x, it's going to tell us the probability we see that. So maybe I say the number of kids in a household, what's the probability I see 3 kids in a household? I put 3 into the probability mass function, it tells me the probability I see exactly 3 kids in a household. Right? So, it's called a function, but if we actually, where did I put my other marker? But it could be as simple of a function of this, right? Usually when we think of like a function, we think of something like that, right? But it could be as simple as this, right? Here's my different outcomes that I could see for x. My probability mass function, if I plug in different values for this random variable x to be equal to, it's just going to spit out at me what those probabilities are. So a probability mass function could be as simple as just a table like this telling you the probabilities associated with each possible outcome for x. So it doesn't have to necessarily have like a functional form, right? It could be as simple as this. Okay. So you'll notice, right, this probability mass function is going to be giving me these different probabilities. I've got essentially x, y coordinates, right? I could, on my x-axis, plot these different values for x, and then do like a little bar graph, right? This goes up to 0.1, this one goes up to 0.15, right? I could use those probabilities to kind of graph out what that distribution looks like. And we've really already done something like this before, right? Here I have probabilities, which are very similar, pretty much the same thing as when I was using relative frequencies, right? So we've really already done something similar to this before. Okay? So we've got this probability mass function. It's going to give us these probabilities different outcomes. So I'll have all these pairs, which I could throw on a graph. But I've also got some things I can think about. So this probability mass function, when it's giving me a probability, so automatically I know it has to be somewhere between 0 and 1, right? It's a probability. At the very lowest, it's 0. At the very highest, it's 1. But I said these probabilities as probability mass function is very similar to relative frequencies. So remember when we said we add up the relative frequency of like every possible outcome for a variable? So when we had like the causes of death data, if we took the relative frequency for every cause of death and added them all up, we said that they should add up to what? 1. Right? So if these probabilities from the probability mass function are similar to relative frequencies, same idea. If I take every possible outcome, so the probability that there's 0 kids in the household, plus the probability there's 1 kid in the household, plus the probability there's 2, add that up to the very last possible outcome, those should all add up to 1, right? Covers every single possible outcome, adds up those probabilities should add up to 1. Okay. So we'll also start playing around with, and not as much for the discrete random variables we'll look at, but definitely after the first exam, we'll start also think about this idea of cumulative, right? So my cumulative mass function just tells me the probability that this random variable x is equal to or less than a certain value, right? So less than or equal to a specific value. So, you know, maybe if I said, think about the number of kids in a household, if I plug in 20 into that cumulative mass function, that's going to tell me the probability that X is less than or equal to 20. So when I'm looking at really high values for X, what should that cumulative mass function be really close to? You use that kind of number of kids in a household to kind of put some context to it. What would you guess the probability that if I chose a household at random, what's the probability they have less than or equal to 20 kids? It's going to be pretty close to 1, right? I mean, that should cover every household, hopefully. I hope there's not a household with more than 20 kids, right? So really high values for X, that cumulative mass function gets really close to 1. If I look at really low values for X, what should that cumulative mass function be close to? Really close to 0, right? So those are kind of, you know, some traits of that cumulative mass function. And we'll start to use this idea of cumulative a little bit more. That's why I'm introducing it here. So I have an example, I think. There we go. So let's say I've got some firm and I've got the number of hires they have over the last 35 years. So there was 2 years where they only hired 1 person, 7 years where they hired 4 people, 9 years where they hired, 4 years where they hired 9 people, and they've never hired double digits, right? So we've got this, you know, this old historical data for this company. I then might be interested, okay, this next year, how many new hires is this company going to have? Well, I can use the historical data to empirically assign probabilities, right? And those probabilities will essentially be my probability mass function. So here, right, for that number of hires being 1, it's 2 of the last 35 years. So 2 over 35, that would be my probability of seeing 1 hire. The probability of seeing 2 hires would be 1 out of the 35 years. The probability of seeing 3 hires, 7 out of 3 of the last 35 years. I basically create relative frequencies. So a lot of the times, all we're doing is using historical data, coming up with relative frequencies, and then empirically assigning those relative frequencies as our probabilities. So it's the same, and we've done this before. This is exactly what we did before when we were coming up with relative frequencies. So there's nothing really new here. Right? It's just for an unexpected or a future kind of outcome as opposed to something that's already been recorded. So I've now got these different X values and their associated probabilities. I kind of already mentioned we could just use those probabilities as our Y-axis, plot these on a bar graph, and kind of get an idea about what the distribution of this variable looks like. Now you can see here 3 and 4 are the most likely outcomes. Not very likely we see anything less than 3, and then everything kind of above 4 up to 9. There's no real pattern, right? They're all kind of likely to, they're somewhat likely to occur, but not as likely as that number of hires being 3 or 4. Okay. Well, if I've got this data, I've got a distribution, I might start to be interested in things like, well, where's the middle part of that distribution, right? Or what's the mean of this random variable? So because this random variable is something that hasn't been realized yet, it's something that doesn't yet have an outcome, right? We'll often call the mean of a discrete random variable the expected value. Okay, so it's what we expect based off the historical data and the probabilities we empirically assign. This is the expected value for this random variable X. Right? When we actually run the experiment, we're only going to see one outcome. Right? In the next year, the company will only hire exactly 5 people or exactly 6, but we're only going to see one of those outcomes occur. But we can come up with a mean or expected value. It's going to be almost identical to something we've already done. Okay. So if I think about the mean of a discrete random variable, this is going to be the formula. Right? So this should look kind of similar. This looks pretty similar to something we've already done. Right? We're just going to go through every single possible value for X and then multiply it by the associated probability, add them all up, and that will give me my mean. So this should look really similar. Oops, I don't want to do that. This should look similar to when we were doing weighted means. Remember, we did the sum of the weights times the X values divided by the sum of the weights. That's all we're really doing here with the mean of a discrete random variable. We're just finding a weighted mean. It's just that now, right, we'll take for our weights the probability that X is equal to a specific value, multiply that by the value for X. Sum of the weights would be the sum of the probabilities, right? But here, if I take the probability of every possible outcome for X, what should those add up to? So if I divide by 1, it doesn't change anything. So I can essentially ignore my denominator now. So for a discrete random variable where our weights are now probabilities, we're really just left with the numerator from our weighted mean equation, right? Because the sum of these weights is 1, and it actually becomes a little bit easier. So finding the mean of a discrete random variable is actually like finding a weighted mean, but almost a little bit easier because we no longer have a denominator. Okay. Any questions on this for keep moving? I'll show you an example here in just a second. Well, if I've got a mean, I've got the middle part of the data, right? How would I kind of apply that to that data set for the number of new hires? Well, I would take the first outcome X, multiply it by the probability it occurs. So 0 times 0, plus the next outcome of 1 times the probability it occurs. So plus 1 times 0.06, plus 2 times 0.03, plus 3 times 0.2, all the way down to the very last possible outcome of 12 here. Okay. So it looks like a lot, when I write it all out, but it's really not too bad, right? I'm just going through multiplying each outcome by its probability or its weight, and then adding them all up. Now in the exam, I had some people ask me in my earlier sections, like, I'm never going to give you a data set that has this many outcomes. Like if I expect you to do this, I'll give you like 3 or 4 outcomes. But as long as you know the process, right? You could do it with 4 outcomes. I know you can do it with 12. It'll just take you longer, right? So I don't want timing to be a big issue on the exam. So I would never give you something quite this large, right? But I would still expect you to know how to kind of go through it and calculate this, okay? So it's a weighted mean, really with no denominator. We can think about it that way. Well, if I've got the middle part of the data, so I get the value of 5.14, so we have something to actually reference. So my mean is 5.14. Maybe I'm also interested, well, what's the variation of the data, right? What's the variation from this expected value? So you can imagine, like if I'm making projections, maybe I want to know what the expected amount of rain is, right? If I'm thinking about like agricultural industries. And so I might have the expected value based off of some data, and maybe it's like 5 inches of rain. However, I know that there's probably variation in that as well. And if it for some reason falls below 3, I'm going to have some issues, right? So I might be interested in kind of the variation from this point, which we can find as well. And it's basically a weighted variance where the denominator just goes away, because the denominator for the weighted variance, remember, was still the sum of the weights. So the sum of my probabilities now are just equal to 1. Okay. So my weighted variance is my variance for a discrete random variable is the same thing as a weighted variance. It's just my denominator basically is always 1. So nothing really new here. And then if I want to find the standard deviation, it's the same as always. I just take the square root of the variance. Okay. So what would this look like? Well, here I would go through, and we've already done this kind of before with weighted variance, just not as many outcomes. Take the first outcome of 0, subtract that mean of 5.14, square it, multiply by the probability we see 0 occur. Then add to that 1 minus the mean of 5.14 squared times the probability we see 1 occur. Do that for every single observation and then add them all up. So if I'm doing this by hand, I probably don't try to enter this all into my calculator at once. I probably break this down into the intermediate steps and write another column. So, 0 minus 5.14 squared times 0, we'll just write that number down. Well, anything times 0 is 0. So write down a 0 there. Next outcome, 1 minus 5.14 squared times 0.06, write that number down. But I kind of break it down into steps, might make it a little bit easier to approach. Okay. Any questions kind of over this? Like I said, this is really almost like review of stuff we've already done. Weighted means, weighted variances. It's almost a little bit easier now because our denominator, we just have a sum of the probabilities will always be 1. Okay. Okay with that? All right, so I've got a couple smaller data set examples where we can kind of talk through this. Hopefully it shouldn't be too bad. So if I'm looking at this, and this is like some discrete random variable for the bonus amount. So like this is some fictitious crazy company where they're giving out huge bonuses. So it could either be 10, 6, or 3 million or 0. And I see the different probabilities associated with seeing each one of those amounts. if I had to guess here, well, first of all, there's definitely a range of values. You can tell me the mean has to be in between here. Now it's a weighted mean, like we're calculating it like a weighted mean, but we're still trying to find the middle part of the data. So if there's two values that you know the mean has to be in between here. It's a wide range, but it has to be somewhere between your minimum and your maximum, right? 10 and 0 here. So, sorry, there was some kind of weird sound there. So you know it has to be somewhere between the minimum and the maximum. Not only that, if I had to guess, I'd probably say it's somewhere in between 3 and 6 million, right? Because those are the two most likely outcomes. Those probabilities will be my weights. They're going to influence the mean the most, right? And I have kind of equal values on either side of those, so I would guess somewhere between 3 and 6 million, right? So if I'm just throwing darts here, I'm going to throw it at either C or D. Okay, but we can actually compute it, right? Go through, take the first outcome of 10, multiply by 0.15, I get 1.5. Write that number down. 6 times 0.25. I get 1.5, write that number down. 3 times 0.4, 1.2. I would then add all those up. If I do that, I get 4.2 million, right? So it's kind of using this to talk through some of the kind of more of the principles behind what we're doing here. Okay. If A was the answer, what would have to be true about the probabilities over here? So if you end up finding the mean here of this discrete random variable, and it was 250,000, what would have to be different about these probabilities for that to be the case? So some of these probabilities would have to be higher, but which ones? That 0 probability would have to be a lot higher, right? And then that would really pull that mean down closer to that 0 value. Okay. So what if instead I asked you for the variance? So we've got that mean of 4.2. How much does this data set vary from that middle point? Well, which of these can I rule out right away? What's the negative? Why? What's the lowest the variance can ever be? Yeah. We said something that has absolutely no variation, that's as low as it can get. So we can never see negative values for our variance. So hopefully on the exam next Friday, right, when you see a problem like this, you automatically just went from 4 possible choices to 3. I would even suggest as you're on the exam, like you see this, cross it out, cross the negative out for if it's asking for a variance, okay? Or if it's asking for a standard deviation, right? Those both have to be positive. Now from there, you just kind of have to do the work. So if I'm, if I'm working through this, kind of what would this look like? And I'll blow this up here in a second. We would take that very first outcome, subtract the mean of 4.2, square it, multiply it by the probability you see that outcome for X. Add to that the next possible outcome, subtract the mean and square it, multiply that by the probability you see, 6 be the value for X. And then we'll just do that for the next 2 outcomes. And I'll blow this up so that you can see it a little bit clearer. Oops, it's a 2. All right. And then once I do that for every outcome, I'm adding them all up. I should get approximately 9.96. So same thing as what we're doing with a weighted variance. It's just we no longer have that denominator. Okay. So this is the variance. What if I wanted the standard deviation? What would that approximately be? Well, how do I go from the variance to the standard deviation? I simply take the square root. So the square root of 9.9 is going to be roughly 3.1-ish or 3.2, somewhere around there. I don't know exactly off the top of my head, but we're right around 3. Okay. Any questions on that before we keep moving? Okay with this? So really, like, not a whole lot of new there. Like, it's really weighted mean, weighted variance, very similar to the relative frequency stuff we were doing. It's just all in a slightly different light now. I'm kind of setting up for the next thing, which is I'm going to skip this and come back to it. The binomial distribution, right? A very specific type of discrete random variable. So these we see them pop up a lot, or we see this distribution a lot because it's anytime we have an experiment that's being run over and over and over again, right? And we'll kind of say, n number of times, right? So maybe I'm flipping a coin 100 times, right? So that would be my number of trials there. I'm just, every coin flip, right, is a trial. I'm running it 100 times. And every single trial, right, every coin flip, I'm going to see one of two outcomes. I'm going to see a success or a failure. For the coin flip example, I see heads or I see tails. These success failures can really be anything, right? So here it's like, heads or tails, I'm flipping a coin. I think I've used examples for like either getting struck by lightning or not, right? Like, so it's these weird, we can make anything a success failure. It's really just what are you looking for and the complement of that, right? Binary, 1, 0, okay? So every trial has a success or failure. And the probability we see success is the same on any trial. So if I flip a coin, on any one coin flip, the probability should be 0.5, right? So we've got this constant probability of success. Whoops. So I've got my number of trials, and then I only have 2 possible outcomes. So this is a setup for a binomial distribution example, okay? So one thing that we're also going to need is that the trials need to be independent. So when I flip the coin the first time, even if I see heads, that doesn't change the probability I see a heads on the second coin flip, okay? So the trials are independent. Then we might have, a very relevant question would be, well, what's the probability if I flip a coin 100 times, what's the probability I see 60 heads out of those 100? Or what's the probability I see 40 of the 100 flips come up heads, right? So I can use some type of probability mass function to tell me the probability of seeing different number of successes out of those n trials. You can imagine, like, if I flip a coin 100 times, 50, like seeing 50 of the 100 coin flips come up heads is going to have probably the highest probability. It's the most likely outcome, number of heads I'll see. And then as I move in either direction, it becomes less and less likely, right? So the probability that 60 of the 100 flips come up heads, well, that's going to be greater than the probability that I see 80 of the 100 come up heads. And that's going to be greater than the probability I see 100 of the 100 come up heads, right? So each different number of successes or number of heads that I see are going to have different probabilities. So the way that I can come up with a probability of seeing 50 out of 100 coin flips come up heads is using this formula here. So it looks a little nasty, and we need to talk through it a little bit so we can give it some more context. So when we start with the examples on Friday, we'll kind of be ready to hit the ground running. So first of all, there's only 3 things in this equation. N, which is the number of trials. So if I'm flipping a coin, say 50 times, N would be 50. I might then be interested in the probability that I see exactly 30 of those 50 coin flips come up heads. So my X, that would be the 30, the number of successes I'm interested in finding the probability of. And then the only other thing is this P, which is the probability of success on any one trial. So flipping a coin, the probability of success on any one coin flip is 0.5. Okay. So I've got my number of successes that I'm interested in finding the probability of, the probability of success on any one trial, and then N, which is my number of trials. Okay. So I think over here, once I have my values and I plug them in, I think we can, can do the, subtraction here. We can raise things to different powers in our calculator. Probably familiar with that. Probably not as familiar with these exclamation points, right? So what do these exclamation points mean? Well, all it is, right? If I take a number and write an exclamation point next to it, that's called a factorial, right? So a factorial, basically, the easiest way to remember it is you start with that number and then you just multiply down to 1, right? So you'll just start with that number and then multiply down to 1. That's our factorial. It's the easiest way to describe it and to think about it. It's not technically the mathematical way to write it out. So what ends up being true is every other number works just like that. You start with a number, multiply down to 1. So 1 factorial would be 1. There's a weird thing that goes on with factorials, though, which is that 0 factorial ends up also being 1. So we treat 0 factorial simply as a 1 as well. So that's why the explanation I give isn't technically like the most technical one. When I say start with a number and multiply down by 1, it's actually a little bit more precise here, right? I can write it out slightly differently, and the way in which it's supposed to mathematically be written is y0 factorial is also 1, okay? But for all intents and purposes, like just think of it as, if I see a factorial, start with that number, multiply all the way down to 1, okay? Any other questions there? I don't think I have anything else on this slide. I think I've got an example here. You're okay with that so far? All right, so one thing that will also pop up is, so I'm going to write one out. So let's say I wanted to find the probability of, out of 100 coin flips, what's the probability it comes up heads twice? I know it's going to be a low probability, but what is the actual probability? So I'm just going to write that formula out, plugging in 100 coin flips, 2 successes, right? Or seeing heads 2 times. And this isn't overly important, but so the x would be 2 times 1 minus probably success n minus x. Okay. So I'm sure we could deal with this in our calculator, right? We could get that entered in, but this part might be a little bit trickier, right? So I'm going to think about this part separately for a second. What I would suggest doing very quickly, especially before the exam, but I would try whatever calculator you plan on using. I would try to find the factorial button on there. Okay. So once, usually like on a TI 83 and 80, all these other ones, it's like second math, then you go over to PRB or prob, I think it's PROB, and then you go down and there's an exclamation point or the factorial button. On other calculators, it's second and one of the buttons that you can see on there. Some calculators have like a PRB button on them, and it's usually under that, or second probability, and the probability is one of the things above one of those keys. So I would suggest looking for that. Now, if you can't find it, you can ask me and I can try to help you out. But I'll tell you what I'm going to do when you ask me, and the easiest way to do it, unless you have a TI 83 or above, just Google whatever calculator it is, factorial button, right? And that's probably exactly what I'm going to do if you come and ask me for help, which is fine. I don't mind doing it. I don't mind helping you find it. But if you can't find it, that's probably also one way that could help. Okay. So the problem is, even once we have this factorial button, if you try to enter this in, your calculator is going to get mad at you. It's going to yell at you and tell you that it can't do it. Right. So 100 factorial, I mean, imagine 100 times 99 times 98. This gets like a massive number very quickly. Right. And your calculator just simply can't do that. Right. This is where we have to be a little bit smarter than the machines. Right. So they'll take over eventually, but not yet. So if I write this out, all right, 100 factorial all the way down to 1, 100 multiply all the way down to 1. 2 factorial is 2 times 1. And then 100 minus 2 is 98. So 98 factorial looks like this. Well, notice everything past 98 is going to cancel. Right? And really all this is 100 times 99 divided by 2 times 1. When you enter it this way into your calculator, it tries to do these factorials first, and it just gets too big and it can't do it. But if you write it out, you can see very quickly a lot of things are going to cancel. I'm left with a pretty simple, right? I mean, this is, a lot more complicated looking, but once I simplify it down, it's really not a whole lot there. Right? So we might have to do that sometimes, right? Our calculator, even if it can't handle it, there's ways that we can actually do it on our own. Okay. Any questions there? Oops, it's going off the screen a little bit there. We're okay with that? All right, so we're really going to hit the ground running with this on Friday. Before we leave today, I have one more thing. We've got some things that we've talked about before that I think is an interesting problem. Actually, before I do that, does anybody know what movie this is from? Big Short. If you guys haven't watched it, all of you should, especially like being in the business school. It is like a very entertaining, but also a very good summary of what went down in the financial crisis of 2008, 2009. And it just makes it entertaining, breaks it down in an easy to digest way. I always tell this story whenever I mention this movie. My sister's like the most bohemian hippie ever. and she enjoyed this movie, like has no idea of any financial jargon or anything. So if she can enjoy it, I'm sure you guys will definitely enjoy it. But we'll kind of finish off with this problem, use some things we talked about. So let's say I've got a room of 40 people or a class of 40 people. And I ask you, what's the probability at least 2 people have the same birthday in that class? 40 people, right? Usually the responses you would get would be somewhere, relatively low, okay? Now if we assume that there's no twins, and that every day is equally as likely, and that nobody's parents were like friends and try to time their kids to be born around the same time, right? Excuse me. Then what would the probability that 2 people have the same birthday out of that class of 40 be? Right? Well, if we think about, and then we get, on a similar vein, if I have a class of 1,000 people, well, it's going to be way more likely 2 people have the same birthday, right? So what number of people in a room do you need to where the probability that 2 people or more have the same birthday goes over that 0.5 barrier, right? So let's think about this in a slightly different way. So if my X is that at least 2 people have the same birthday, that's the same as 1 minus the complement. So what would the complement be? Well, if at least 2 people have the same birthday, the complement of that would be that nobody has the same birthday, right? So I can find the probability that nobody has the same birthday, subtract it from 1, and that'll give me the probability that at least 2 people have the same birthday, right? Or that there's at least one day that has a shared birthday. So what we're going to do to find the probability of X complement, that nobody has the same birthday, is go through every person and say, what's the probability they have a unique birthday? Well, the very first person, right? I haven't asked anybody else yet what their birthday is. So there's 365 available days out of 365 days. So their probability of having a unique birthday is 1. I then ask the next person. Well, now the probability they have a unique birthday, there's only 364 remaining unique days. So their probability of having a unique birthday, 364 out of 365. And the next person, 363 out of 365, all the way down to that 40th person, right? So why did I do this? Because this will help me if I think about if these births are independent. One thing in that video I posted in light of the snow day is that if we have independent events, the probability of the intersection is just taking the probability of each event and multiplying it by each other. So if I want the probability that the first person has a unique birthday and, right, or intersection with the second person has a unique birthday and the third person has a unique birthday, all I'm going to go through and do is multiply the probability that the first person has a unique birthday, second person has a unique birthday, third person has a unique birthday, all the way to the 40th person in the class, right? So if I do that, here, right? So that's all I'm doing here, right? Taking the probability each person in the class has a unique birthday when I'm asking them. And if you do a little bit of algebra, what you find is actually a situation like this actually follows a component or part of that binomial. Like this will look very similar to some things that we were looking at in the binomial distribution. It's a little bit different, right? But you can kind of see similarities. So if I enter this in my calculator, I get the probability that everybody has a unique birthday is about 0.1. Which means the probability that at least one day is shared as a birthday between 2 people is 1 minus that, or as high as the probability is almost 0.9, right? So in a room of 40 people, the probability that at least 2 people have the same birthday is actually 0.9, which to me is like a very counterintuitive result. I would not expect it to be near that high, right? And you can play around with this. You can play around with rooms of different size. So if you do that, right, what you'll find out is right at 23 people, is where that probability crosses over to be above 0.5. So anytime you were in a room with more than 23 people, it would always be smart to bet that 2 people have the same birthday. At least 2 people have the same birthday in that room, right? And I'm sure there's a way to bet with people and make a lot of money off this knowledge. If you do it, please let me know. But kind of these counterintuitive results are always fun. And this was really just using the idea of complements and independence to come up with this, okay? So we'll pick up with binomial distribution on Friday, go through a bunch of examples, and maybe even introduce the last kind of type of variable we'll talk about, which is the Poisson, okay? So remember that online quiz will be posted once I get back to my office, due before we start class on Friday.